Hi Research Design and Analysis students, welcome back. Today's mini lecture is going to be on regression. For the last week or so we've been focusing on correlation and figuring out a basic statistic we can use to talk about how two variables go together. So when correlation is positive, as one factor goes up, the other one goes up, or if one goes down, the other goes down. And in a negative or inverse relationship, they're moving in the opposite direction. So as one goes up, the other goes down, or vice versa. Today we're going to look at regression, which is one way to look at two or more factors to help predict an outcome. So I'm going to move over here in the corner and kind of get me out of the way. That way you can see me gesturing if you like to know I'm still here. And we're going to take a look at the learning objectives for this content, and then talk a little bit about regression. So when we finish out this section, we should be able to define linear regression, predictor variables, criterion variable, the standard error, the estimate, identify how regression is similar to and different from correlation, describe multiple regression by explaining when this approach would be used, identify what is unique about stepwise multiple regression as a statistical test, and explain when structural equation modeling is a good tool to use in research. Please understand, for Psych 2231, we will not do any computational work for this chapter. I do want you to know why we might use these statistics and what they can do for you, but we're not going to be able to do these kind of statistics. This would come in an upper-level stats course or when you get to graduate school. So, regression is a kind of relationship statistic. We have some different statistics, like t-test. Does this group differ from that group? Z-tests, does this group or person differ from that group? Regression is one of those correlational kind of approaches. What is the relationship between this thing and that thing? If we have a correlational statistic, we are simply looking at the relationship between two factors, A and B. Regression goes half a step further and helps tell us how to predict what might happen in that second outcome by knowing what we do about that first outcome. So what's unique about regression is that it gives us a formula to help tell us what amount of a variance is accounted for in factor B when we know factor A. If you think about it, folks like insurance agents use this all the time. Actuarial science is based on making predictions about what people's behavior is going to be like. So they use a mathematical formula to figure out if you do these things, this is your risk for, say, having a car accident or dying early if we were selling life insurance. And so we use factors and what we know about them to predict likely outcomes. So it is based on a correlation, but the thing about regression is we can use multiple factors at the same time. So what they have in common is that they're a relationship kind of statistic. What is unique is that regression builds upon correlation to help us predict one step for the other. So a simple linear regression still only uses two variables. It's a tool that lets us predict an individual's score on the dependent or outcome variable from their score on the independent variable. And we will then look at how we might want to know more than one predictor for a particular outcome. For example, if we think about a health outcome like blood pressure, right? There have been correlational studies that found a relationship between weight and blood pressure. So if we have a correlation between these two things, we know that weight and blood pressure tend to go together. When people's weight go up, their blood pressure tends to go up. That's a positive correlation. When people weigh less, their blood pressure tends to go down. So if we were using a correlational statistic and study, we can know that these two things are connected, but we can't tell which one changes the other, or we're not using really one to predict a change in the other. When we start asking questions with linear regression, we are starting to imply that we know more of a cause. If we change this thing, then it will result in a change in this thing. If we change our weight, if we make our weight go down, then we are also hoping our blood pressure goes down. Or if we change the amount of oatmeal we eat each week, our blood pressure will tend to go down. That might be a negative relationship. So with regression, we are sometimes theoretically deciding one of these causes the other and trying to set up a statistic that helps us see when we make that change does that help us know more about the outcome? So you'll notice that the language, when we talk about regression, down here, I'm trying to get my cursor back, is a little bit more causal than you're used to seeing the language for correlational studies. Alright, so mathematically, just so you know what's going on, we can represent regression, being able to predict one variable from the other, by a mathematical formula. And that formula is y with a little hat, which is the predicted value of your dependent variable, is equal to a, which is the place where our line crosses the y-intercept or y-axis, plus b times x. This is the slope of the line and our score on the first variable. So I'm not having you calculate these by hand, but I want you to know that this is what the formula that comes into play when we take raw data like this. Do we see a relationship between how many absences students have from class and their exam score, which tend to have kind of a relationship? And so here is an example of a regression line that we can fit from each person by plotting their 2 points to figure out our y hat equals a plus bx. Right? That'll help give us the slope and direction of the line to see whether it's a positive or negative relationship or prediction. If it's positive, it'll go this way. If it's negative, it'll go this way. If we have no correlation, we'll see a big cloud, or that line will be fairly flat. All right. And if you're into the math, I'll kind of go through here. There are steps in my PowerPoint that help talk about how to calculate that slope line. When we do regression and correlation, we tend to let SPS do it for us, right? And it can fit that line of best fit or regression line across our scatter plot. We don't have to know a whole lot of points of data, maybe 3 or more, to get a line that helps tell us the connection between those two things. But the more points we have, the better. And that regression line, right, y hat equals a plus bx, helps show us the average relationship we have across the two variables of interest, and it gives us an idea of how far each person's score would be off of that line. So the stronger the correlation or regression value, the more tightly clustered those dots will be, right? It'll be a nice tight cloud, or if it was a perfect relationship, a straight line left or right. And then if we have a weaker relationship or no relationship, you'll see a bigger cloud of dots around that fit line. So one of the other things we can look at is the standard error of the estimate, which tells us what's the typical distance from each person from that average line of fit across everybody. And just like we looked at in z-tests, a smaller standard error, which is a kind of deviation, means we have less variability in that data. In other words, in this case, less scatter around our line of fit. So this first example has a smaller standard error, a smaller scatter around the line, than this one does. See the bigger cloud here? This would have a larger standard error of the estimate. So this one, with a tighter cloud, is going to make a stronger prediction about the outcome because we have less spread. We have more dots clustering around that line. Alright, so regression like we're looking at here, being able to predict one factor from another based on how they're related, is different than something you might see in other places called regression to the mean, which is a testing phenomenon where if we're scoring people twice, they tend to come back to, regress towards, the mean the second time we test them. So extreme scores tend to become less extreme if we measure again. Regression here is about moving backwards. Like a toddler can regress if they've been potty training and then they start having accidents again. So that score is moving in a way that is maybe not so phenomenal. Okay? So that's just kind of a sidebar talking about the other way we sometimes hear the word regression used. The other neat thing about regression is that we can use it in more complex models. So we looked for a minute at a simple linear regression, how those two things fit together from variable A to B. But we might think about an outcome where we really want to predict one particular dependent variable outcome from multiple independent or predictor variables. Maybe we know that the number of car accidents that you get into has something to do with your age and how many speeding tickets you've had and your gender, and whether you own a red sports car. And if we know all of those things together, we have a better way to predict what your outcome's going to be. Mathematically, that kind of statistical formula we'd use to test that idea is called a multiple regression. It's a way to do a fit line for an outcome, but using multiple pieces to see how each one of these predicts the outcome. And we can see then, relatively speaking, which one of these are the stronger or best predictors. If we were using multiple regression to predict blood pressure, like we did a couple slides ago, we might want to know about people's weight, but also the salt in their diet, and how much fatty snacks they eat, and how much exercise they're getting, and whether they have a family risk of high blood pressure, and whether they have a stressful job, and whether, right, etc., etc. So again, what's neat about multiple regression is it adds in a number of pieces to predict that outcome. If we did multiple regression, first what it would do is look at the correlation or relationship between each of the pieces. So this is a correlation matrix that shows here's our job performance outcome, here's the other things we think might be related to it. It's first going to see if each piece is related, then it will put them into a bigger model and figure out what are our best predictors to get to that outcome. Okay. If we're adding multiple pieces in, we might be interested in a statistic called the coefficient of determination, or R squared. And what we do is take the R, the correlation value between whatever factor and the outcome, and we square it. When we do that, we can see how much of the variation in the outcome is explained by each of the pieces. So again, this is why we would use multiple regression and multiple factors as a prediction tool, because real life doesn't just rely on two things. Any behaviors that we see for people or situations tend to be pretty complex, and so while we're interested in B and we want to know if A goes into that, we also would have C and D and 3,649 other things that might come in. So we might have a theory or a situation where we want to know those multiple pieces and predicting the outcome. Alright, so just a couple things to wrap for today. In SPSS, if we were doing this and running a multiple regression, we would be able to see then whether each piece that we put in is a good predictor in the model of the outcome. If so, we'll have a relatively big number here, closer to 1 than 0. And we'll also be able to square that to figure out how much of the variance it can explain. And then there's some other pieces here that we could look at. This is for the overall model to see how everything we put in predicts the outcome. And then in our second piece, we can look at each of those independent variables to see if it is a good predictor of the outcome. If each factor is a good predictor, we'll have a bigger B here and a smaller significance. So in this case, all three of these things, an IQ test, small significance. If the P is low, reject the HO. The job motivation test, small significance. Outcome of the social support test, small significance. So each of these is a good predictor of job performance. Alright, so we talked about weight and blood pressure, and again, the reasons we might want to have complex models. There's a couple other stats I want you to know about really quick that can be helpful for complex modeling. One is a stepwise multiple regression, where instead of you deciding, I'm going to put this in, and this in, and this in, all at the same time, you can load all your factors in and tell the computer mathematically to say, hey, which one is most important? Let's consider that first. And then show me which one is the next biggest factor, and put that in as a second step, and the next one as a third step. And then, if we're not getting any better at predicting the outcome, just leave the other stuff out. So it is really good if you've got a theory of what to expect to use a stepwise regression, or if not, to explore and find out what your strongest predictors are. Regression is also the base, and correlations are for structural equation modeling, where you can fit in lots of different variables to see how this leads to this, and this, and this. And when we do structural equation modeling, it looks a bit like a big set of fireworks. Right? So here's a structural equation model that wants to figure out if parenting relates to kids' adjustment, but it's got a whole lot of stuff going into it as factors. So a really multiple factor study. Thanks, guys. Hope this helps give you an overview of regression.